Hello everyone, today I will bring you the second section of RISC-V CH32V208 Bluetooth Low Energy Quick Start, BLE Protocol Stack and Peripheral role. This section contains the following three parts: BLE Protocol Stack, Peripheral role initialization, and development and debugging. Let's talk about part 1 first, BLE Protocol Stack. The figure on the right is a block diagram of the BLE protocol stack, which mainly consists of three parts: controller, host, and application. Each of these basic building blocks of the protocol stack is split into several layers that provide the functionality required to operate. Next, the different parts that make up the BLE protocol stack will be described from bottom to top. The first is the physical layer. The physical layer is the part that actually contains the analog communication circuitry, capable of modulating and demodulating analog signals and transforming them into digital symbols. BLE uses the 2.4 GHz ISM band to communicate. The frequency range of this frequency band is from 2.400 GHz to 2.4835 GHz. It is the only frequency that is available in all countries without a license. Wi-Fi, classic Bluetooth, and ZigBee also use this frequency band. BLE divides this band into 40 channels from 2.400 GHz to 2.4800 GHz. As shown in the figure, 37 of these channels are used for connection data, and the last three channels, 37, 38, and 39, are used as advertising channels to set up connections and send broadcast data. Channels 37, 38, and 39 are not three consecutive channels, and their frequencies differ greatly. In this way, the probability that the three channels are interfered at the same time is very low. The modulation chosen to encode the bitstream over the air is Gaussian frequency shift keying. The modulation rate for BLE can be selected as 1 megabit per second or 2 megabits per second. The second is the link layer. It is responsible for advertising, scanning, creating or maintaining connections, and making sure packets are organized correctly. The third is the host control interface. It transports commands and events between the host and the controller. The fourth is the logical link control and adaptation protocol. It supports higher-level protocol multiplexing, packet segmentation, and reassembly, and the conveying of quality of service information. The fifth is the security manager. It defines the protocol and behavior to manage pairing, authentication, and encryption between devices. The sixth is the attribute protocol. The attribute protocol defines two roles, server and client. Each device is a client, a server, or both. It allows a server to expose a set of attributes to a client that are accessible using the attribute protocol. A client requests data from a server, and a server sends data to clients. Each server contains data organized in the form of attributes, each of which is assigned a 16-bit attribute handle, a universally unique identifier, a set of permissions, and a value. The attribute handle is simply an identifier used to access an attribute value. The UUID specifies the type and nature of the data contained in the value. When a client wants to read or write attribute values from or to a server, it issues a read or write request to the server with the handle. The server will respond with the attribute value or an acknowledgement. The 6 attribute protocol PDUs defined by ATT: request, response, command, notification, indication, and confirmation. Requests sent to a server by a client that invoke a response. Responses sent to a client by a server in response to a request. Commands sent to a server by a client that do not invoke a response. Unsolicited notifications sent to a client by a server that do not invoke a confirmation. Unsolicited indications sent to a client by a server that invoke a confirmation. confirmations sent to a server by a client to confirm receipt of an indication. The seventh is the generic attribute profiler. Generic attribute profiler is built on top of the attribute protocol and establishes common operations and a framework for the data transported and stored by the attribute protocol. JTT specifies the format of data contained on the JTT server. Attributes as transported by the attribute protocol are formatted as services and characteristics. Services may contain a collection of characteristics. Characteristics contain a single value and any number of descriptors describing the characteristics value. The picture on the right is JTT-based profile hierarchy. The JTT profiler specifies the structure in which profile data is exchanged. This structure defines basic elements such as services and characteristics used in a profile. The top level of the hierarchy is the profiler. A profiler is composed of one or more services necessary to fulfill a use case. A service is composed of characteristics or references to other services. Each characteristic contains a value and may contain optional information about the value. Solid boxes are mandatory components. Dashed boxes are optional components. JTT profiler defines several features. Each of the features is mapped to procedures and sub-procedures. These procedures and sub-procedures describe how the attribute protocol is used to accomplish the corresponding feature. The picture below is a profile example of heart rate. It includes a heart rate service and device information service. The heart rate service contains a measurement characteristic. 19.8 is the recorded measurement value. Notify is the property of this value, which means that the measurement value only can be notified to the client through the server. User descriptor is a descriptor of this characteristic, which is a set of strings. The device information service contains a characteristic that stores system ID, and this characteristic only allows the client to initiate a read request to obtain the information. The eighth is the generic access profiler. The GIP layer is responsible for connection functionality. This layer handles the access modes and the procedures of the device, including device discovery, link establishment, link termination, initiation of security features, and device configuration. In standby state, the device is in the initial idle state upon reset. In advertiser state, the device is advertising with specific data, letting any initiating devices know that it is a connectable device. In scanner state, when receiving the advertisement, the scanning device sends a scan request to the advertiser. The advertiser responds with a scan response. The process is called device discovery. The scanning device is aware of the advertising device and can initiate a connection with it. In initiator state, when initiating, the initiator must specify a peer device address to which to connect. If an advertisement is received matching that address of the peer device, the initiating device then sends out a request to establish a connection. In slave or master state, when a connection is formed, the device functions as a slave if the advertiser and master if the initiator. The ninth is the application. It is responsible for containing the logic, user interface, and data handling of everything related to the actual use case that the application implements. Then talk about part 2, Peripheral initialization. Advertising is the peripheral's way of enabling the central to discover itself. Every time the peripheral advertises, it will send the same advertisement date on the 3 broadcast channels, 37, 38, and 39. Then wait for the advertising interval to start the advertisement again. Advertisements can be divided into 4 event types, which are connectable undirected event, connectable directed event, non-connectable undirected event, and scannable undirected event. They all have different properties. Connectable undirected event can respond to scan requests and connect requests. Our peripheral routines use this advertisement event type. Connectable directed event do not respond to scan requests and only respond to connect requests from centers with matching addresses. Non-connectable undirected event will neither respond to any scan requests nor connect requests. Scannable undirected event will respond to scan requests but not connect requests. After the central scans the advertisement data of the peripheral, it can obtain the scan response data by sending a scan request. Take a look at this picture. This is where the peripheral first advertises on channel 37, then continue advertising on channel 38. After the peripheral finishes sending the advertising data, it will switch to the data receiving state. The central scans the advertising data on channel 38 and then initiates a scan request. After receiving the scan request, the peripheral will send a scan response. After the response is completed, the peripheral will continue to advertise on channel 39. BLE can save power because of the existence of connection intervals, and the allowable range of intervals here is 7.5 milliseconds to 4 seconds. That is to say, BLE can communicate up to 4 seconds once, and the longest time for each communication is only a few milliseconds, and the rest of the time is running at extremely low power consumption. So this is why some BLE devices can work for 1 to 2 years with the button batteries. In order to further reduce power consumption, BLE also introduces the concept of slave latency. The slave can skip several connection events. That is, the slave does not need to respond after the master sends a packet. The premise is that the slave has no data to send to the master, and the slave will respond if there is data. This again reduces some power consumption. The number of slave latency ranges from 0 to 499, and it must be less than or equal to the timeout divided by the connection interval multiplied by 2 and minus 1. The timeout means that if there is no successful communication between the master and slave within the timeout period, the connection will be considered disconnected. The timeout range is from 100 milliseconds to 32 seconds. There is a restrictive relationship between the connection interval, the slave latency, and the timeout. Then talk about part 3, development and debugging. The template project we created in the previous section is a peripheral routine. We will explain based on this project next. Look at the main function. This function is the initialization of the delay function. The delay function is realized by the system tick timer. The value assigned by this function to the POS and PMS variables is how many system tick timer clock cycles are occupied by 1 microsecond and 1 millisecond, respectively. The clock period of the system tick timer is HCLK divided by 8 by default. HCLK is the 19.6 MHz system clock, so 1 microsecond is equal to the system clock divided by 8 million, and the obtained value is the number of cycles occupied. This function is the initialization of the serial port function. ULT1 is selected by default. You can switch the serial port for printing debugging information by switching the macro definition of debug. If you don't need to print debugging information, you can comment out this macro definition. This function is the initialization of the BLE protocol stack. Here is the comparison of whether the header file of the Bluetooth library and the Bluetooth library match. If it doesn't match, it will not continue to run. Here is to set the 32 MHz crystal load capacitor. Because the external high-speed clock input pin of CH32V208 has a built-in load capacitor, the size can be selected through the program. Appropriate load capacitor can make the 32 MHz output by the crystal oscillator more accurately. Next, start to set the structure of the Bluetooth protocol stack initialization. The memory address variable here sets the address of the RAM space allocated to the Bluetooth protocol stack. The space size is 7 kilobytes. The memory length variable here sets the size of the RAM space occupied by the Bluetooth protocol stack, which is 7 kilobytes. The size can be modified according to the actual situation of the project. The buffer max length variable here sets the maximum packet length allowed to be sent in Bluetooth communication at one time, as the allowable range is 27 to 516 bytes. The default configuration is 27 bytes. When the central and the peripheral negotiate the packet length, the one with the smaller packet length shall prevail. Therefore, the peripheral is configured as 27, and the central and peripheral can only communicate with 27-byte packets. And if both central and peripheral are configured as 516 bytes, then they can negotiate any packet length between 27 and 516. However, the length range that can actually be reserved for the application layer to transfer data here is 20 to 509, because 7 bytes need to be used as protocol overhead. The buffer number variable here sets the number of packets that the controller buffer can receive. Generally, the central or peripheral puts the send data and receive data in the buffer and waits for the idle time to send or notify the upper layer of the received data. The default setting is 5. The text number event variable here sets the number of the packets that can be sent in a connection event. The default setting is 1 packet, and the maximum number of the packets that can be cached by the buffer cannot be exceeded. The text power here is the transmission power of the Bluetooth radio frequency. The default setting is 0 dBm. The greater the power, the greater the signal strength, but the power consumption will increase accordingly. The powers that can be selected are -18 dBm, -10 dBm, -5 dBm, -3 dBm, 0 dBm, 1 dBm, 2 dBm, 3 dBm, 4 dBm, 5 dBm, 6 dBm, and 7 dBm. The SMV address variable here sets the flash start address reserved for the Bluetooth protocol stack to store bounding information. The SMV number variable here sets the number of bounding information to be stored. The bounding information of each device needs to occupy 256 bytes of space. The default setting here is 3. That is, the flash space occupied by the bounding information is 768 bytes. The read flash callback variable here and the write flash callback variable below sets the callback function of reading flash and writing flash. Because the bounding information is stored in the flash, it is necessary to tell the Bluetooth protocol stack how to read or write the bounding information to the flash. The clock frequency variable here says the clock frequency used by TMOS to run at 16 kHz, because the running clock of TMOS comes from RTC, as RTC clock initialization is 32 kHz divided by 2. The clock accuracy variable here says the clock accuracy. 1000 ppm means that the 32 kHz clock will deviate by 1 time every 1000 vibrations. Because the internal 32 kHz is set here, the accuracy is slightly lower. If an external 32 kHz is used, the clock accuracy can be increased to 50 ppm. Vibration 20,000 times, only 1 deviation. The clock accuracy set here affects the time when the central and peripheral opens the sending or receiving channel. For example, the central and peripheral agree to communicate again after 1 second. However, the peripheral cannot open the transmit window exactly after 1 second. It may have to advance 0.1 second, that is, open the transmit window after timing 0.9 second. Because the clock of the central and the peripheral have errors, the sending and receiving should take the error time into account. This part of the work is done by the Bluetooth protocol stack, and the application layer only needs to tell the protocol stack the clock accuracy. The connect number variable here says the number of the connections. Byte 0 and byte 1 says the number of centrals that can be connected at the same time. The remaining bytes says the number of peripherals that can be connected at the same time. The TS callback variables here says the chip internal temperature sampling callback function. The purpose is to allow the Bluetooth protocol stack to perform a clock calibration when the chip temperature changes by more than 7 degrees Celsius. Because when the temperature changes, the frequency of RF and RC will change. The RC callback variable here says the callback function for internal 32 kHz clock calibration. The idle callback variable sets the idle sleep callback function. The purpose is to reduce power consumption by entering the stop sleep mode when TMOS is idle. In the sleep function, first calculate the arrival time of the latest event in the future, and use this time to enable the RTC timing interrupt. When the chip enters the stop sleep mode, after the RTC timing interrupt is triggered, the chip wakes up and continues to execute the program. The routine doesn't enable the idle sleep function by default. The MAC address variable is to set the MAC address of Bluetooth. The address assigned to the chip by the manufacturer can be used, or the address can be customized by the user. The MAC address assigned to the chip by the manufacturer is unique globally. The setting of common parameters has been completed here. Use the BLE lib init function to initialize the Bluetooth protocol stack. The clock for CRC function is turned on here. These two enable Bluetooth-related interrupts. This function is the initialization of the hardware. The previous video has already talked about it, so I won't go into details. The important thing is the registration of the clock calibration event and the initialization of the RTC clock. This is the initialization function of the GIP role task, completed by the Bluetooth protocol stack. Just call it. This function initializes some peripheral role parameters. First, look at which events are registered. These events are all related to the peripheral role. The first is a mandatory system message delivery event. The second is an event to start the peripheral. The third is an event that periodically sends data. The fourth is an event of connection parameter update. The fifth is an event of communication speed update. The sixth is an event to get the signal strength. The detailed event function will be discussed later when this event is called. Let's take a look at which parameters are initialized. The parameters related to the GIP role are set using this function. This function has three formal parameters. The first is the parameter type. The second is the byte size of the value. And the third is the address of the set value. Let's look at the code. This is to set whether the peripheral advertisement is enabled or not. The size of the setting value is 1 byte. Only true or false can be set. This value is the address of the variable. This is to set the scan response data. This is the byte size of the scan response data. This is the address of the scan response data. This is to set the advertising data. This is the byte size of the advertising data. This is the address of the advertising data. The organization of the two data has a fixed format. Let's take a look. The maximum size of advertising and scan response data is only 31 bytes. The data is internally composed of structures. Each structure contains a length section and a data section. The length part identifies the length of the data part of the structure. The data type is placed at the beginning of the data part, followed by valid data. The structures included in the advertisement data and scan response data are optional. Even advertisement data and scan response data may not be set. If it is not set, the peripheral will send an empty advertisement package after startup, and the central will still scan the peripheral. The advertisement data in the routine includes the advertisement type flag and the UID of the custom service. The scan response data contains the name of the peripheral, connection interval, and transmit power. This is to set the minimum connection interval and the maximum connection interval after the central and the peripheral are connected. The formal parameter description of this function is the same as that of the previous function. It is used to modify the characteristic in the GIP service. This is to set the device name characteristic in the GIP service. It is recommended that the device name set here be the same as the name contained in the advertising data. About the GIP service, we will talk about it next. This function has only two formal parameters. The first is the parameter type, and the second is the value to set. This is to set the minimum and maximum value of the advertising interval, and the time unit is 625 microseconds. The advertising interval set by default in the routine is 50 milliseconds. This is to set whether to enable the reporting of receiving central scan requests. Only the information of the central that initiated the scanning requests is reported to the application layer, and the scanning response is still automatically completed by the protocol stack. The parameters related to pairing and bounding are set here. The function has three formal parameters. The first is the parameter type. The second is the byte size of the value. And the third is the address of the set value. This is to set the pairing passcode. If the central wants to pair with the peripheral, it needs to send this passcode to pair successfully. This is to set the pairing mode. The default setting is to wait for the central to initiate a pairing request. You can also choose not to allow pairing or initiate a pairing request by the peripheral. This is to set whether to enable the function of preventing man-in-the-middle attacks. Preventing man-in-the-middle attacks is a security feature that prevents the key from being obtained by a third device during the pairing process. This is to set the input and output capability of the peripheral. That is, the way to input or output the passcode. The default setting of the routine is no input function, but the passcode can be output for display. This is to set whether to enable bonding. After enabling it, the peripheral will save the pairing information to the flash, and the central doesn't need to repair when it connects next time. Here is to add services to the profile. The first is to add the JP service, which is mandatory in a peripheral. The second is to add the JT service. The third is to add the device information service. The fourth is to add custom service. We mainly use this custom service. A total of the above 4 services are configured in the peripheral routine. The first 2 services are built in the Bluetooth protocol stack, and some of their characteristics can be configured through the API interface. The contents of the later 2 services are all in the profile folder of the project, and all can be customized. We mainly look at the fourth one, custom service, as the other services don't need to be modified if there are no special requirements. Let's look at the third function first. This is a function for registering a service. There are 4 formal parameters. The first formal parameter is the service table, which is the body of the custom service. Take a look at the contents of the table. This is an array of structures consisting of 4 parts. The first is the UID. The second is permission, which refers to the permission of the value item in the structure. The third is the handle. The fourth is the value address. Next, let's look at the meaning of each structure. The first is the structure of the service type. This is a UID. The front is the length of UID, divided into 16 bits and 128 bits. The following is the UID that defines the type of the attribute structure, which is OX2800. The UID mentioned here should be distinguished from the service UID to be mentioned soon. Next are the permissions for the values contained in the attribute structure. Here is read permission. This is the handle value. The handle value is uniformly assigned by the protocol stack when the service is registered. This is the address of the value contained in the structure. The value here is the UID of the custom service. The value of UID is defined by the user as OXFFEO. The second is the structure of the characteristic declaration type, and the UID is OX2803. This is the permission of the value contained in the structure, which is the read permission. The value contained in this structure is a property of the characteristic value contained in this characteristic, which is said to be readable and writable. That is, this value describes the permission of this, and this value describes the permission of this. The third is a structure of characteristic value type. Here, the UID identifying this type is customized and is OXFFE1. This is the permission of the value contained in the structure, which is readable and writable. It should be consistent with the permissions described above. The value saved here is a meaningful value. The size is 1 byte. It can be the heart rate or the number of steps. It is completely defined by the user. The fourth is the structure of the characteristic description type, and the UID is 0x2901. This is the permission of the value contained in the structure. The value contained here is the description of this characteristic, which is a string. These three structures make up a complete characteristic. The following characteristics 2 and 3 are similar to characteristic 1. Let's look at characteristic 4. In characteristic 4, the value contained in the characteristic declaration structure is written as the notify property. This is the characteristic value structure of characteristic 4, and the UID is OXFFE4. No permissions. Because the value is sent by the peripheral, no permissions is required. There is one more structure here than other characteristics. This is a structure of client characteristic configuration type, and its UID is OX2902. This structure is used to enable peripheral notifications to the central. By default, the peripheral cannot notify the central of data, and the central needs to enable the peripheral to notify itself of data. The way to enable is that the central writes 1 to the value contained in this structure. This value is a structure array including 4 structures, which can be used as the flags of whether the 4 centrals allow notification. Before sending a notification to a central, the peripheral will judge whether 1 is written in the structure corresponding to the central. This is the characteristic description type structure of characteristic 4, which is the same as the same type mentioned before. Characteristic 5 is similar to characteristic 1, 2, and 3. Only the permission in the characteristic value structure have changed. The reading here requires authentication. It is necessary to enter a passcode for pairing, as the reading operation can only be performed after the pairing is successful. Let's continue to look at the service registration function. The second formal parameter passes the size in bytes occupied by the service table. The third parameter passed is the encryption key length. The fourth formal parameter passed is a callback function for reading and writing characteristic values. When the central reads and writes the characteristics of the peripheral will call this function to process it. Let's look at the read callback function. First, judge whether the offset value is greater than 0. The offset here means to start reading from the offset byte of the characteristic value, because the length of the characteristic value is smaller than the length of the MTU. All the data can be read in one package, so no offset is needed. Then, according to the UID, it is judged which characteristic value is read. Just put the characteristic value into the cache address provided by the protocol stack. Finally, returns a read status. Let's look at the writing callback functions. It is similar to the process of reading. First, judge whether authorization is required. Then, judge whether there is an offset or exceed the length of the characteristic value. If all conditions are met, the data written by the central is copied to the characteristic value. A callback function is also called here to handle what happens when the characteristic is written to a new value. This callback function is here. This string will be printed if characteristic 1 is written with the value. This string will be printed if characteristic 3 is written with the value. The location of registering this callback function is in another place, and I will talk about it later. There is a difference in the type of writing. This UID is OX2902, which is a UID that the central enables the peripheral to notify. When the central writes values into this attribute, this function is called and all values written by the central are passed to the formal parameters. The operation of enabling the peripheral notify is handled by the protocol stack. The service registration function is finished. Look at the above two functions. The first one is to initialize the attribute of the client characteristic configuration, and the protocol stack will assign initial values to this structure. The second is to register a callback function. When the central is disconnected, the client characteristic configuration structure assigned to the central will be initialized. Then we come back here. This part of the code assigns initial values to each characteristic value in the service. It's just a simple copy. Here is the structure for initializing the peripheral connection parameters. This structure contains the connection handle, connection interval, slave latency, and timeout. If you want to save some other information, you can add it to the structure. This registers a callback function that is called when the characteristic value is changed. It is a processing function that will be called when the central writes to the peripheral we just mentioned. Here is the registration advertisement callback function. The routine is not initialized by default. The first one is useless in the peripheral. The second is to put the callback function that receives the central scanning request. That is, the peripheral will call this callback function after receiving the scan request from the central, which is the same as the function enabled here. It is just that the functions that the protocol stack will call are different. After enabling here, the function here is called by the protocol stack. The above is all the initialization of the peripheral. All the functions of the peripheral must be more than that. There are also some functions that are not used or just use the default value, so they are not mentioned. We will talk about it later when it is used in other routines. The next step is to set the peripheral startup event, which will be executed immediately after the TMOS starts running. Back to the main function. Next, the while loop is executed and the TMOS starts to run. Now, a total of 2 tasks are initialized in TMOS. One is the task here, which will only periodically call the clock calibration event. The other is the task of the peripheral. The peripheral starts event is set. Let's take a look at the peripheral start event. The function called by this event passes 3 parameters to the protocol stack. The first is the ID of the task that receives the message. The second is bounding related callbacks. One is the callback function for the pairing passcode. If not registered, use the default passcode, 6 zeros. The other is the callback function of the bounding state. It is used to tell the application layer that it is currently pairing start, pairing completion, bounding completion, or bounding back connection. Not registering will not affect device bounding. The third is the callback function related to the peripheral role. One is the callback function of the peripheral state. This state is peripheral initialization completed. This state is the start of advertising from the peripheral. This state is that the peripheral has been connected to the central. This state is when the peripheral connected to the central and the peripheral starts advertising. This state is that the advertisement is not turned on after the initialization of the peripheral completed. This state is an error occurred. One is the callback function to get the RSSI value. Generally, the application layer calls the function to obtain the RSSI value once. After the controller is obtained, it is reported to the application layer through this callback function. One is the peripheral parameter update callback function. This callback function will be called when the connection interval, slave latency, or timeout of the peripheral changed with the central negotiation. Next, we download the program to the development board of CH32V208. Through the information printed by the serial port, we can see the running process of the peripheral. The Bluetooth library version number printed on the first line. All initialization has been completed before the second line is printed, and TMOS starts running. The second and third lines are the information printed by the peripheral state change callback function. First, the initialization of the peripheral is completed, and then the peripheral starts advertising. After the peripheral starts advertising, the nearby centros can scan its advertising data and initiate a scanning request. After the fourth line, the MAC addresses of the centros that initiated the scan request are printed. Use the BLE debugging app to connect the peripheral. The second picture is the peripheral device scanned by the app. The app displays the name of the peripheral, the MAC address of the peripheral, and the RSSI of the peripheral. The name here is the device name set in the scan response data. Click on the name. You can see all the advertisement data and scan response data of the peripheral. Click Connect to connect to the peripheral. After the connection is complete, all initialized services will be displayed. Take a look at the serial port print information. First, the peripheral receives the connection request to start the connection, and then the connection is completed. It's the code here that prints these two lines of information. First, enter the state of connection completion. If a central has already been connected before connecting to this central, disconnect the currently connected central. Otherwise, save the state of the current connection. Save the connection handle, connection interval, slave latency, and timeout. Here, 3 events are started. The first is periodic events. This event is executed every 1 second. The content is to notify the central of 1 byte of data. The second is the parameter update request event. Execute after timing 4 seconds. The requested parameters are the connection interval ranging from 7.5 milliseconds to 125 milliseconds, the slave latency being 0, and the timeout being 1 second. The third event is the RSSI get event. Get it every 2 seconds. The above 3 events are all timed tasks. They are executed after 1 second, 4 seconds, and 2 seconds, respectively. After the function finishes executing, it prints connected. Lines 4 and 5 print the message that the central initiates a connection parameter update request. Line 6 and 7 print the obtained RSSI value. Line 8 prints the message of the connection parameter request initiated by the peripheral. Notify related information can be viewed in the app. Click on the arrow behind the characteristic 4. The window shown in the second picture pops up. The peripheral program has been periodically calling the notification event, but the app has not received any data because the central does not enable notification. After the peripheral notification is enabled, the app receives the data notified by the peripheral. The upward arrow in the app is to write data to the peripheral, and the downward arrow is to read data from the peripheral. In the picture on the left, the app writes OX55 to peripheral characteristic 1. The peripheral calls the callback function of the change of the characteristic value and outputs the information of the change of the characteristic 1 value through the serial port. The picture on the right shows that the app reads data from characteristic 1 of the peripheral. Let's see how the code runs after disconnection. Click disconnect in the upper corner of the app. This is the print of the serial port. After the peripheral was disconnected, it reported the status of disconnection and restarted the advertisement. When the connection is disconnected, the code here is executed. Enter the waiting state when the connection is disconnected and execute this function. This function clears the connection parameters and stops two events that will execute periodically. Then restart advertising. The peripheral enters the advertising state. The content of this section ends here. Thank you everyone.